Alright, so welcome back to our last example of a reduction. This time we are going to talk about subset sum, which is a problem that we have seen before, and we have even developed a dynamic programming based algorithm for it. So let me just recap the problem for you. The input is a collection of numbers, n numbers w1 through wn, and we have a target which we will denote by t, and the question is there a subset of these numbers whose sum is exactly t? Right? And if you remember, we've seen a dynamic programming algorithm for this whose running time is n times t. Asymptotically, it's n times t. And the question that we talked about back then as well was if it's fair to treat that as a polynomial running time. And if you remember, we had a little discussion about what it means to have a pseudo-polynomial running time, which is essentially to say that the running time is indeed polynomial, assuming that the numbers involved are also polynomially bounded, right? Remember that these numbers are actually expressed in binary, which means that there could be an explosion in terms of magnitude. So if you have a number which occupies b bits of memory, the number that it can express can be as large as roughly 2 to the b. So if you do anything in your algorithm which relies or depends or is proportionate to the magnitude of the numbers involved, then you could be experiencing an exponential blow up. So that's something to keep in mind, and that's what was happening with our dynamic programming algorithm as well. So in fact, if we do exploit the full power of this exponential expression, this sort of the succinctness that is afforded to us by binary representations, it turns out that this problem is actually hard. And what we are going to see is actually a reduction from the three-dimensional matching problem, which was the problem we last encountered, to the subset sum problem. So remember that for three-dimensional matching, we have three sets, A, B, and C, which are disjoint. And let's say they all have n elements each, which we are going to denote A1 through AN, B1 through BN, and C1 through CN. And what we are given is triplets from A cross B cross C, which is to say we have these ordered triples. And we want to know if there is a selection of triples from among the given ones, which is such that when you look at the union of those, you see that every element in A union B union C appears exactly once. So that's our source problem, and we're going to try and reduce this to subset sum. So remember that subset sum is a problem about numbers, so we have to somehow translate these triples into some sort of a numeric form of expression. So can you think of ways in which we can associate numbers with triples? It's probably not very intuitive, but let me give you a hint here. So whenever you're dealing with a set, right? So let's say you have a universe U and a subset of U. Let's say this universe consists of elements E1, E2, up to En, and your subset, let's say, is something like maybe E3, E5, E9, E13, E17, something like this. Now, one way to represent the subset is, of course, by listing out the elements like we just did. Another way to represent it is what's called the characteristic vector representation, which you may have come across before in your other courses. The way the characteristic vector works is that it's going to be a vector with n coordinates, and all the coordinates which correspond to elements that belong to the set. So for example, 3, 5, 9, 13, 17. All these coordinates are going to be 1 in the vector, and all the other coordinates are going to be 0. Right? So just to say that a little more precisely, or in notation if you like, the vector associated with S, its ith coordinate is going to be 1 if and only if E sub I belongs to S, and that's for I in the range of 1 to n, given that our universe has elements E1 through En. So that's the characteristic vector representation. It's basically a bit vector, and that's, well, now that you have a bit vector, you can potentially think of it as a number expressed in binary or in some other base. So you have some way of associating a set with a number, with a vector, which is then associated with a number. And these triples are really, you can think of them as specialized subsets of A union B union C. I say specialized because, well, it's not just any subset. We know that the subsets that we are interested in have exactly 3 elements, and they have exactly 1 from the set A, 1 from the set B, and 1 from the set C. But nonetheless, they are subsets. So see if you can play around with the characteristic vector representation and see if that gets you anywhere. Take a pause here and really puzzle out this reduction a little bit and come back once you've done that. All right, so, well, let's move on and take a look at the reduction that I do want to propose. We are actually going to associate with each triplet its characteristic vector. So the dimension of our vectors is going to be 3n because our universe is 3n elements, right? And for instance, if the triple in question is A3, B1, C4, what we're going to do is we're going to have the third bit set to 1. And then after that, well, the first bit of the second chunk, right? So that's 1 offset by 5. So that's going to be the 6th bit also being set to 1. And similarly, we're also going to have, well, C4 would be the last but 1 bit, right? We have 15 bits altogether. So the 14th bit is also going to be set to 1. Now, if you want to read this off as a number in some base, then, well, we have to sort of index all these bits here. And indexing starts from 0 just to make it convenient to translate into numbers. And if you want to read off this in base D, then that's just going to be the sum of powers of D, where the powers are given by the indices that are triggered to 1. So of course you could read this off in base 2, but as we will see, base 2 is probably not the most useful base to work with, because let's think about what we want these numbers to mean, or what do we want out of this reduction. What we want is a yes instance of subset sum if and only if there is a perfect 3-dimensional matching, right? Now, if you think about, well, it's usually easier to think in terms of the forward direction when you're trying to come up with a construction. So if you think about what it means that we have a perfect 3-dimensional matching, it means that each element in the universe appears exactly once in the collection of sets that we're looking at. So if you write down the bit vector representations corresponding to, the sets of a perfect 3-dimensional matching, what will happen is if you go through it column by column, then you'll see that each column has exactly 1, 1. And then in some sense, if you add up the vectors, right, what would you expect to see? You would expect to see the all ones vector with these 3n coordinates, right? So this in some sense is your target vector. But of course, we're not doing vector addition here. We're doing, we're adding numbers. So, well, if you think of these numbers as simply being binary numbers, you will have no problem with the forward implication. So if you do have a perfect 3-dimensional matching and you look at the corresponding binary numbers, if you add them up, you will get the all ones vector. So that's perfectly fine because every column has just 1, 1, and you don't have to worry about annoying things like carries and so on. However, in the reverse direction, if somebody gives you a bunch of these binary numbers which add up to the all ones, the number represented by all ones in binary, well, then it's really not clear if you're getting the 1 because you have a 1 in that column somewhere, or if you're getting it as a result of a carry from, the next column. And so you may not really have a faithful representation of a matching if you interpret these numbers in binary. So we have to do something slightly different with these numbers. The main issue in the reverse direction is the carries. So one way to not have to worry about carries is to just avoid them altogether. And that sounds like a simple idea, and it's actually a neat trick in this case. How do you avoid worrying about carries, or how do you avoid having carries if you can help it? Well, one way to do that is to interpret these numbers in a base that is so large that you're never going to carry over. So remember that you're generating one of these numbers for every triplet in the input, and the input to our instance has m triples. That's where we are coming from in the 3D matching instance. So let's just interpret very generously. Let's interpret our numbers in base m plus 1. Okay, so we set this d to be m plus 1. What this will ensure for us is that when you're adding numbers in base m plus 1, and you only have m numbers, so some subset of m numbers is still at most m numbers, you will never have to fiddle around with carries. And now if you want that the outcome is, the all ones vector in base m plus 1, then, well, in that case, the only way to do it is to ensure that you have exactly 1 in every column, because there's no carries that will provide you with those extra ones. And that's essentially the heart of the argument. If you want to be explicit about what is the target sum, you can in fact write that out, and that's going to be, well, we run through our indices from 0 to, notice that's going to be 3n minus 1 here, because we have n slots, 1 for each of A, B, and C. Indexing starts from 0, so we have 3n minus 1. And since we are interpreting this in base m plus 1, the magnitude of the number that we are after, the number which is all ones in base m plus 1, that's going to be m plus 1 to the I summed over all of these indices, right? So that's our target number, and all of our numbers are to be interpreted as these numbers in base m plus 1, and that's about it. So we know that subset sum is at least as hard to figure out as 3D matching is. And we do have a little bit of a discussion left still. I want to make sure that we appreciate the nuance about subset sum being hard versus the algorithm that we saw earlier. So here's an example just to test our intuition. Consider this problem. You're given a graph G, which is not necessarily connected. In fact, this question is interesting only when G is not connected. So we have a graph G and we have a number K. And we want to know, does there exist a subset of connected components whose union is exactly K in terms of size, right? So can you find me some subset of connected components so that if I count the vertices in these chosen components, the total number of vertices I have is exactly K. Now this must sound very familiar. It must sound a lot like subset sum actually. And what we can do is we can in fact reduce this to subset sum. We can say, well, look, we're going to have, one number for every connected component, and that number is going to be the size of that component. And you can convince yourself that this is a valid reduction to subset sum. But we've always said there's no point in reducing to a hard problem. We've just seen that subset sum is hard. So perhaps this reduction to subset sum is not useful. So we can reduce this to subset sum. But notice that you can also reduce subset sum to this problem. So let's try to do that as well. So how do you reduce subset sum to this problem? So if I have the number wi, I can simply introduce a connected component. It could be a path or a complete graph. Pick your favorite style. But you could introduce a connected component of size wi on wi many vertices, right? And again, you can convince yourself that you have an instance of subset sum which is valid if and only if you can actually pick out components whose collective sizes add up to the target value of subset sum. You just make sure that this number K here matches the target in the subset sum instance. That's all you have to do. So now we're reducing from a hard problem to this one. Does that show that this problem is hard? Think about that for a minute before making your bets, and think carefully, given all our discussion about, pseudo-polynomial running times and efficient representations, and crucially the fact that these reductions, for them to be useful and valid, have to be efficient reductions. They have to be polynomial time reductions. So take your time, think about that, and come back to this once you've had a chance to think about this a little bit. Okay, so it turns out that the reduction from subset sum is actually not a valid reduction. And the reason for that is that it's going to be too expensive for you to construct a connected component of size wi. Remember that in the subset sum world, wi simply takes log of wi many bits to write down. But if you have to describe a connected component of a graph which has wi many vertices, then you have to write down, whatever your favorite representation of the graph is. It could be an adjacency list or an adjacency matrix or an edge list. Whatever you choose, you're going to have to write down at least wi units of information, something proportional to that. And that's already an exponential blow up. So this reduction is too expensive. It's a valid reduction in the sense that it preserves equivalence. And it's a well-defined reduction, but it's too expensive. We can't afford this, coming from a general instance of subset sum. Now, what about this other reduction here where we said we will reduce two subset sum? That seemed like a valid reduction but not very useful because we seem to be reducing to a hard problem. However, notice that the instance of subset sum that we generate from this graph instance is actually an instance where all the numbers are bounded by n, which is the size of the graph that we are starting with, right? So in some sense, the way the graph is expressed, right, that gives us the license to spend the kind of time that the dynamic programming algorithm needed, which is n times t. But remember that t itself here is actually k. And remember that this number k cannot be more than n, right, for the total number of vertices. Because if k is more than the total number of vertices, we can immediately say no, it's a trivial problem. So as a result, this dynamic programming algorithm that we had, which I kept saying is pseudo-polynomial, in this particular case, for this specialized problem, it's actually a purely polynomial time algorithm, right? So all our numbers are nice and bounded. The target is also bounded. And so this is actually a useful reduction. We reduced it to subset sum. We can employ the dynamic programming algorithm that we already know to actually solve this problem. So whenever you're dealing with problems involving numbers, you do have to be a little bit mindful about where things are going, how big are the numbers in question. And remember that subset sum is easy if the numbers are small, but it's hard in general, as we saw by the reduction from 3D matching. Okay, so that's all I will have to say about specific problems. At some point, we may have some more supplementary material with additional practice reductions to look at, but I hope that the reductions that we have seen so far have been palatable and have given you a general sense of how we do reductions. So by now you've seen two kinds of reductions, ones that we use for actually solving the problem, like we reduced to instances of network flow previous week, and here, for instance, right now we reduced some problem, which is something to do with counting sizes of graph components, to a specialized instance of subset sum, which we know how to solve. So reducing to a problem that you already know a good algorithm for is one way to use reductions. The other prominent way to use reductions is to reduce from problems that are already expected to be intractable. That way you establish at least conditional intractability of your problem, and you say, well, I can't solve my problem, but nobody else can either very likely solve my problem. So that's the other way to use reductions, and we've seen a couple of examples of those this week. Now we will run this off with a short concluding commentary on useful starting points for reductions. We have mostly reduced from 3SAT, but there are other fun problems that you can reduce from, and I'll just run through some of them with you in a short concluding video. So that's what's up next, and that will be a wrap on this week. So thanks, and I look forward to seeing you in one final discussion.